Welcome to the unit on the binomial expansion. In this unit, we will be looking at using partial fractions. The objectives for this session are to use partial fractions to expand fractional expressions. Some algebraic expressions can be expressed as expansions. So, for example, root 4 minus 5x can be expressed as shown, and 1 minus x to the power 2/3 can be expressed as shown here. The expansions of difficult expressions can be simplified with partial fractions. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to split 7 plus 3x all over 1 plus x times 1 minus x into partial fractions. So let's solve this. We're going to begin by letting this expression be identical to a over 1 plus x plus b over 1 minus x. Adding the two fractions on the right-hand side gives us this expression here. Notice that the denominators on both sides of the identity are the same. Therefore, we can conclude that the numerators are identical also. We are going to proceed and try to find the values of a and b. Begin by letting x equal minus 1. When we plug in x equals minus 1 in the left-hand side, we obtain 4. When we plug it into the right-hand side, we obtain 2a. And of course the b term now disappears. This is why we plugged in x equals minus 1 in the first place, in order to make this term disappear completely, so that we're left with a on the right-hand side and a number on the left-hand side. And so we have that 2a is equal to 4, which implies that a equals 2. Now let's look at trying to find b. This time we're going to plug in x equals 1. When we plug in x equals 1 on the left-hand side, we obtain 10. And when we plug in x equals 1 on the right-hand side, we obtain 2b. Notice that this time the a term has completely disappeared, and this of course is why we chose the value x equals 1. So now we have that 2b is equal to 10. And of course this implies that b equals 5. We now have our values of a and b, and we simply plug those in as shown to give us this expression for 7 plus 3x all over 1 plus x times 1 minus x. Now let's take a look at part B. We are required to show that the cubic approximation of 7 plus 3x all over 1 minus x squared is as shown on your screen. So let's solve this. From part A, we know that our fraction 7 plus 3x all over 1 minus x squared is identical to these two partial fractions added together. Two over 1 plus x is equal to 2 times 1 plus x to the minus 1, and 5 over 1 minus x is equal to 5 times 1 minus x to the power minus 1. We can now express both sets of brackets on the right-hand side as expansions. Let's consider the first set of brackets on the right-hand side first. 1 plus x to the power minus 1 can be expressed as the expansion shown on your screen. We've plugged in n equals -1 into the right-hand side, as shown here, here, and here. And of course we leave x as it is, because x is the same in the theoretical part and in the example, as shown here. For the second pair of brackets, n is equal to -1 again, so we plug in n equals -1 here, here, and here. However, the plus x in the theoretical part has been replaced by a -x in our example, and so we replace on the right-hand side the x by -x, as shown. So we have these two expansions on the right-hand side. Plugging this in gives us this expression here. We're only going to take the first 4 terms of the expansions, as we're required to show that our fraction is equal to a cubic approximation. And similarly, plugging in the expansion for 5 times 1 minus x to the power -1 gives us the expression shown. And finally, tidying up gives us the required cubic. And now for part C, we are required to write down the range of values of x for which the expansion is valid. So let's solve this. Of course, from parts A and B, we know that our fraction can be expressed as an approximation to this cubic as shown. The expansion of 2 times 1 plus x to the -1 is valid if mod x is less than 1. And the expansion of 5 times 1 minus x to the -1 is valid if mod -x is less than 1. Of course, mod -x is the same as mod x. And therefore we can conclude that 2 times 1 plus x to the -1 plus 5 times 1 minus x to the -1 is valid when mod x is less than 1. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. We are given that the quadratic approximation of 6 over 1 plus 5x minus 4 over 1 minus 3x is 2 minus 42x plus 114x squared. We are required to write down the range of values of x for which the expansion is valid. So let's solve this. The expansion 6 times 1 plus 5x to the -1, which is of course the first fraction, is valid if mod 5x is less than 1. This of course implies that mod x is less than 1 over 5. If we express this in our diagram, it will look something like this. For the second fraction, the expansion of 4 times 1 minus 3x to the -1 is valid if mod minus 3x is less than 1. Of course, mod minus 3x is the same as mod 3x, and therefore we have that mod x must be less than 1/3 for the expansion of 4 times 1 minus 3x to the minus 1 to be valid. Diagrammatically, this can be represented as shown on your screen. So in order for both inequalities to be satisfied, x must lie in the range of both of these lines. So in particular, mod x must be less than 1 over 5. This brings us to the end of this session. If you have understood its contents, you should be able to use partial fractions to expand fractional expressions. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.